So I recently updated the website. So the first thing that I should say is actually a correction that I said last time, and I posted this on the Discord and I posted this on the website, but just in case you were only following along with the videos, which would be very confusing if you're following along with the videos, not with like the documents on the website. On Tuesday, I claimed that a simply connected space is contractible. But this is false. And the counterexample is, say, S2. Right? This is a simply connected space which is not contractible. And if you're just like, Jacob, why is it not contractible? If it was contractible, its homology would be the same as a point, but its homology is not the same as a point. Right? So it's not contractible. Okay. Cool. So just to make sure that that correction's on the official record, it's there. I'm recording the video, so that way it'll be on the YouTube channel, and then future people on YouTube maybe will like comment on the old video and be like, Jacob, you're wrong. And then they'll watch the next video and be like, oh, so I don't know. Okay, so on Tuesday, this first problem was suggested. That we talk about mock qual 0 question 3, and then some people emailed me and asked about these other 5 questions. Were there any other questions that people would like to add to this list?
I could do exercises to know C6. I thought that one was kind of interesting.
Weren't we gonna also go over from the last mock qual? Hold on, what was it? Problem 4.
Oh, yeah. And we should probably do that first since we haven't talked about that. 3, 4. Right, because we did not get to that problem on Tuesday. Okay. No promises that I will make it to all of these problems, but we will certainly try to talk about these problems a little bit. Anything else before we dive in? All right, well, maybe we'll get started, and if there are more problems towards the end, people can bring them up. So yeah, let's start by talking about mock qual 3 number 4. So mock 3 number 4. So the first thing to note if F is surjective, then we're done. Right? Okay, so this problem here states that if I have a continuous injective function from a sphere to itself, then my function is a homeomorphism, right? That's what I want to show, right? However, my domain is compact and my codomain is Hausdorff, right? So we have a theorem, right, which says if f from x to y is a continuous bijection, with X compact and Y Hausdorff, then F is a homeomorphism. Okay. And honestly, now that I'm looking at this, this theorem should have been on the exercises to know document because it's one of those tools which is really useful. But the proof is quite easy. Since it's a bijection, showing that the inverse is continuous is the same as showing that the original function is open. And also, since it's bijection, showing that the original function is open is the same as showing that the original function is closed. And then it's easy to see why this map is a closed map. You take a closed set of the domain. Since your domain is compact, that closed set is compact. So the image of that closed set is compact, but compact sets in Hausdorff spaces are closed. So therefore the image is a closed set. Therefore this function is closed, right? So I guess that the proof outline is F inverse continuous if and only if F open, if and only if F closed, then C subset X closed implies C subset X compact, which implies F of C subset Y compact, which implies F of C subset Y closed. Okay, cool. So it is enough to show that this function is surjective. We would like to use invariance of domain for this problem, and invariance of domain says something about functions from Euclidean space to Euclidean space. Right? So if I say, for contradiction, assume F is not surjective, then there exists Q in Sn such that Q is not an element of the image of F. Let H from Sn minus Q into Rn be a homeo. No. Okay, so now the idea is that I have a function f from Sn to Sn, which is continuous and one-to-one. And now I have a function h to Rn, which is a homeomorphism, right? And I can view f as a continuous one-to-one map from Sn to Sn without Q, because Q is not in the image of f. Okay? So if you just joined us, we're talking about mock qual 3, question 4. Mock qual 3 question. Okay. So the idea, or if I draw this as a picture, right, I have the circle. This maps into the circle without a point. And this is the same as, or in for, I'll draw the picture for n equals 1. This just maps into R, right? The idea is that I'm going to take small open sets, and these small open sets via charts are going to be just open subsets of R. Okay, and then using this chart with F and H, by doing a composition, I'm going to get a map from an open set of Rn to Rn. And by invariance of domain, this will show that the image is open in Rn. Right? Then since H is a homeomorphism, that means that the image of this set under F was open in Sn. Okay, so so we want to show f of H composed f of Sn is open. Oh boy, I haven't gone through the details of this in a little bit. So I guess that one way that I could do this is to show that it's the union of two open sets. Yeah, okay. So let P be an element of Sn be arbitrary. Then let GP, G minus P be homeos, where G of P is a homeomorphism from Rn to Sn set minus P, and G minus P is a homeomorphism from Rn to Sn minus S of P. Then, let's see, H compose, F compose, GP, and H compose, F compose, G minus P are continuous one-to-one maps from Rn to Rn. So H compose F compose GP of Rn and H compose F compose G negative P of Rn are open by invariance of domain. There we go. This seems like a reasonable argument. Note though, H compose F compose GP of Rn union H compose F compose G inverse P of Rn is equal to right, that if I take the union of these two sets, I just get the image of Sn under H compose F, right? So the picture, because the pictures are nice, right? So here I have P and here I have minus P. This goes via F to Sn without Q. This here is Q, and this goes to Rn. So here I have Rn, or maybe colors are better. This goes to all the points except P, and this here goes to all the points except minus P, right? And so that means that this green map goes to like, I don't know, all the points except goes to like some set here, and this goes to, I don't know, some set here. You know, like, actually, this isn't how this could happen because I'm just removing a point. I don't know, it's some subset, right? Okay, but the two subsets together form the entire image of H composed with F. Okay, now that I'm thinking about this, maybe like the green set maps to like here, and the red set maps to like here, or something like this, right? This is probably the more accurate picture. Okay, hopefully this is believable. Right, because the only point that this meets, the only point that G of P misses is P, and the only point that G of P, G of negative P misses is negative P. So the union of these two don't miss any points. Okay, I think that I've over-explained that sufficiently. Okay, so thus H compose F of Sn is a compact subset of Rn, since Sn is compact. H compose F is continuous. So H compose F of Sn is closed in Rn, but then H compose F of Sn is a clopen compact non-empty subset of Rn, but no such subsets exist. Okay, cool. So that shows that this map can't be non-surjective. So therefore, the map has to be surjective.
So I had a question about this because I think I used I don't think it's right using the invariance of domain the way that I did because I double checked the definition and it said that I need open sets in Rn, but then I checked Wolfram, and Wolfram Math World says the domain invariance theorem is true for n manifolds without boundary. So my thought was, oh, let me use that on Sn to Sn to show that, like, I think if I assume that statement of the theorem where I don't have to be dealing with Rn specifically, I can do the proof in a way that doesn't require us to invoke charts and such. Can I share my screen and maybe
Yeah. So basically, by using charts, you can turn a map between manifolds into a map between Euclidean spaces, right? Because it is enough to show that a function is open by showing that it is open on a basis. Right, because then the image of any arbitrary open set is just the image of the union of a bunch of basic open sets. Yeah. So these are certainly, feel free to share your screen, but that's why these two statements are the same. And the reason that I would have used the language of charts for this problem, but this problem appears in part B, right? And you don't talk about charts in part B, so I tried to write a solution that doesn't use charts, right? But yeah, but you're right. There is a version of variance of domain, which is just if you're mapping an n manifold to an n manifold, which is continuous and injective, then it's an open map, right? Anyway, feel free to take the floor.
hello, can you guys
Oh,
seem-
we have two versions of rule. At least I have two versions of rule.
Yeah, sorry, I don't know why I got, can you, I don't know, can you kick the one that isn't talking?
I'll put the one that is talking in the waiting room.
Okay. So like, so yeah, so the thing is, at first I did it and I think I just did it wrong because I did it with the idea that, oh, I can just use invariance of domain, and I forgot that I need a restriction on the domains to be open. But then like now I'm looking at Wolfram Math World and I'm thinking maybe it's still valid. So if you have Sn to Sn by f, which is continuous and one-to-one, these are I can apply invariance of domain to this. F of Sn is open in itself. So
Mhm.
this is open in Sn.
Yes.
So then Sn, however, is compact. So it's also, so this is open,
Hmm.
but it's also compact, which means it's closed. So it's open and closed. Sn is connected. So f of Sn is equal to Sn.
Yep.
Okay. And technically, I guess this statement, the way I justified it, is wrong, but actually right.
Yeah. So yes, this problem does get much simplified if you use the domain invariance theorem for manifolds, which is I just looked up Wolfram Math World, and that's what it calls it, the domain invariance theorem, which is the same as invariance of domain. They just switched the two words.
And technically, you have to take care of, this is for only n strictly bigger than 0, but then the case n equals 0 is trivial because it's a finite set.
Yeah, the only way to inject a 2-point set into a 2-point set is by bijection. Okay, then there's a second half to this question. Should we talk about the second half or should we move on?
I mean, it's like 2 lines for the second half, right? Like you say, oh, well, consider the inclusion from Sn into Sm that appends the appropriate number of zeros. This means that F compose the inclusion is a continuous one-to-one map from Sn to Sn, hence a homeo by the first part. But now you've got that, like, what are you going to do with the rest of SM? You're going to have to collide with points, so it's not continuous or it's not injective.
That sounds better than what I was going to do. I was again going to just like remove a point from the image and a point from the domain and be like, hey, now this is a continuous one-to-one map from Rm to Rn, and we can't have those when m is bigger than n. But yeah, so one way that I can do this is just, yeah, so we can include the second half. Let f from S, what did I say? Sm from Sn be continuous and one-to-one. Then let iota from Sn to SM be inclusion. Just say like onto an equator. Okay. So I'm generalizing what it means to like include S1 into S2 by just choosing an equator. Right. But that's why I put equator in quotes. Right? Or you just, if you write SM as m+1 coordinates, then you're just including into the n+1 coordinates, right? Then let's see. Yeah, I want to do I first. So F compose I is a continuous one-to-one map. F compose iota, which sends Sn to Sn. So F compose iota is a homeo, but that implies that F is surjective, right? Because this is a composition of two functions is bijective. That means that the left function is surjective, right? But then F is a homeomorphism, which it can't be. Because then it is a surjective, continuous, bijective function from a compact set to a Hausdorff set, which means that it is a homeomorphism again. Right?
Oh, I mean, I wasn't even invoking that. I was just saying, well, you know, F composed I hits every point in Sn, but we told us that it's one-to-one. This is now a contradiction because every point in Sn has already been assigned a preimage. And you have more stuff left to assign.
Oh, sure. Just choose a point in SM, which is not in Sn.
Yeah.
Okay, sure.
And you've still got to put it somewhere. But all
Sure. Yeah, lots of contradictions. Cool. All right, questions, comments, or concerns? Or complaints? All right, so then we also had mock quals 0, question 3. Okay. Okay. Topological space is normal given any disjoint closed subsets C. Okay, so first off, I'm going to define some terms just for your edification. So normal, actually, let's start with Hausdorff. between 2 points, I can find an open set, 2 disjoint open sets separating the 2 points. We're proving something which is called normal, which says that between 2 disjoint closed sets, I can find disjoint open sets separating the 2. There is a condition in the middle here called regular, which states that between a point and a closed set, I can find disjoint open sets separating the 2. Right. And then there's like a T1 condition down here, which says that between any 2 points, I can find an open set around 1, which separates it from the other. And then there's a T0 condition, which states that I can find an open set around 1 or an open set around the other, but I don't know which one is the open set.
Jacob,
Whereas
can you
with
say
T1
regular real quick? What was regular again?
Regular says that if I have a point which is disjoint from a closed set,
Okay,
I can find 2 open sets which separate them.
perfect.
And then like T2 is Hausdorff, T3 is regular and T1. Normal is, sorry, T4 is normal and T1. So that there are a bunch of these separation axioms, and who cares? The way that we're going to do this is we're going to show that first we imply regular and then we imply normal, because this is going to help us organize the proof in a slightly nicer way. But this is your roadmap, like at the different points, this is what we're doing. So let's talk about the proof. So let's let C and D be disjoint closed subsets of X. Oh boy. Okay, U is the thing which contains C. So for every C in C and every little d and capital D, there exists U, actually here, just so that I'm not having 2 for everys at the beginning of my proof, I'm gonna say fix C in C. Okay, so I'm gonna prove that this space is regular by showing that, so what I'm going to show, right, is that here I have my C, here I have my D. I'm going to choose a point, little c. I'm going to find an open set around little c and an open set around capital D such that this set is disjoint from this set. What I won't know is that this capital D is disjoint from capital C, right? Like it could be that this is the open set that I get around capital D at this point, right? But it's going to be something which is around capital D and something which is around little point C, and that's going to be my goal, right? So for every D and capital D, there exists disjoint open sets U sub D, V sub D, such that C is contained in UD and D is contained in VD. Note VD for D and D is an open cover for capital D. Since X is compact and D is closed, D is compact. So there exists a finite subcover V E I equals 1 to n. Now define U sub C to be equal to the intersection I equals 1 to n of the UDI, and define V sub C to be the union for I equals 1 to n of the VDI. Right. So going back to the picture, what I've done, okay, it's not letting me change colors because for every point in D, this capital D, this capital C, right? I have chosen a neighborhood, right, around that point, such that all of these neighborhoods are disjoint from a bunch of different neighborhoods around my special chosen point here, right? And so it might be that like the third open set here intersects the seventh open set here, but that's fine, right? Because I'm going to take the intersection of all the ones around my special point C, and that means, right? So all that I'm going to say here is that by construction, UC, VC are disjoint, open, and little c is an element of UC, and capital D is contained in VC. Okay, that's exactly what I've chosen these open sets to do. And so what I've done is I've shown that my set is regular, right? I took an arbitrary open, an arbitrary closed set D, and the fact that little c was in capital C didn't matter at all. So I've taken an arbitrary point, which is away from D, and I've shown that I can find an open set around D and an open set around my point, which are disjoint. Okay? So at this point, I have shown that my space is regular. Now I'm going to use these sets to show that my space is normal, right? Which is going to entitle me almost word for word repeating this paragraph. So now repeat the above construction for every C in C. Then UC for C in C is an open cover for capital C. Capital C is compact because it's a closed subset of a compact space, right? So there exists a finite subcover, say UCJ, J equals 1 to M. Right. So now I have that C is being covered in a bunch of open sets, but now all of my other open sets are open sets which completely cover capital D, right? So Now, if I take the intersection of all the sets which cover capital D, I will still cover capital D. If I take the union of my finite cover for C, I will have a cover for C. And that's going to be the entire proof, right? To find U to be equal to the union, J equals 1 to M of UCJ, and V to be the intersection, J equals 1 to M of VCJ. Then U, V are open, disjoint, and C is contained in U, and B is contained in V. And I think on my qual, I actually proved all three of these statements for both paragraphs, but that would take more time, so I'm not going to here. Questions, comments, or concerns? Or complaints?
Why would you have to prove all three of those statements? Aren't all three of them by construction?
Right, so now I feel confident just saying by construction this is true, because I've cooked up these sets to be exactly the sets that I wanted to. But on the qual, I was like, I want there to be zero reason why they would want to take off points in any capacity. So I don't want them to be like, you have to explain this and take off some points. So I just explained everything. I don't know, I can look up my qual and see if I wrote that much detail, but but that's why I would have proved these three. I don't know, like, I think that the fact that they are open is obvious, right? Because it's a finite union and a finite intersection of open sets respectively, right? The fact that C is contained in U and B is contained in V, I also think is pretty clear, right? Because U was a cover of C. So by definition, the union of all of those things covers C. And D is contained in every VC. So the intersection of all those things still contains the intersection of D with itself a finite number of times, right? So that's also clear. So now, if I were to prove this, I think that the only thing that I would spend time proving would just be verifying that these two sets are still disjoint, right? That because I had a pair, right? The pairs of these things were disjoint. So I would just show that if I take a union of a bunch of stuff over here and an intersection of those corresponding stuff, that those are still disjoint. That might be the only thing that I would still prove if I would be this disjoint in this condition. But luckily, you only have to prove that they're disjoint once, because when you do it up here, you just write the same sentence, right? It really is the same deal. I'm just pretending like capital D is a point in this second paragraph. So, okay, cool. So what was next? Oh, what happened to all my text? Oh, there it is, just popped back in. Mock qual 1, number 7. And the person who sent me this email specifically asked, is there a way to do this problem using partitions of unity? So that's how we're going to view this problem, which is great. So, okay, so M is a positive dimensional smooth manifold. Okay, when I was thinking of my solution to this, I was like, wait, what if, I mean, if this is 0 dimensional, then I don't think this is true. Okay, so, okay. Okay, so in order to use partitions of unity, we need the following easy to prove fact, right? Okay, so there's first, I'm gonna make a claim, which is that M contains an infinite number of points.
Well, yeah, because
Yeah, right.
every subsets are, there's a non-empty subset that is isomorphic to Rn.
Right, yeah, and an open interval in Rn has an infinite number of points, right? So that's not weird, right? So I'm going to start off this proof, which is going to be different from the proof that Raoul wrote, because I'm going to use partitions of unity, but a lot of the themes are going to be there. So proof, so I'm going to let n and n be arbitrary. Let P1 up to Pn be n distinct points in capital M. Let phi n, or let's say B 3 0. I can't remember for a chart if you put the chart first or the open set first. Phi n be a collection of disjoint regular balls around our PI. So, i.e., phi I is a map from B3 of 0 into M such that phi I of 0 is equal to PI and phi I of B3 of 0 intersect phi J, B3 of 0 is the empty set. So I have my manifold, which I will just draw as some surface. It's totally a surface.
Jacob, what does that say on the right? It looks like it got squished.
It does look like it got squished. The intersection of these two things is empty.
Is in B?
Is empty.
Empty. Okay, sorry. And then also, what's a regular ball?
A regular ball is a ball of radius 3.
Okay.
Okay. More formally, when you cover something by regular balls, the reason that I call this regular balls because I want to use a bump function on this, but normally when I do like a cover of regular balls, it's a collection of charts from balls of radius 3 so that the restriction to the balls of radius 1 is still a cover for your manifold. And the reason that you do this is because when you do examples using like partitions of unity with bump functions, right, you want where your bump function is equal to 1 to be a cover for your manifold, right? And then like away from where the cover of from where the function is equal to 1, right? It smooths down to 0, right? And so you can actually use balls of any radius to do this, but Fred likes to use balls of radius 3. So I use balls of radius 3. Okay, so I have n distinct points with regular balls around them. All right, let's call phi I be a bump function around pi, specifically a smooth map phi I, which has the following properties. From M to, I guess I can define it to R, where phi I P, it's equal to 0 if P is in M set minus phi I of B3, 0. It is equal to 1 if P is in phi I with the ball of radius 1 around 0. And it is X, where X is strictly between 0 and 1 else. Phi is smooth. And right, so the function you should be thinking of is like so this is 3 and this is 0. Like before 0 and after 3 it does this thing. There's like a way to turn this function, which Fred constructs in his class. It is constructible. It's like an infinitely differentiable function, which is constant for negative values, or maybe you have to have that it's constant for values less than 1. Actually, for this function, you do need values less than 1. So let me just redraw the map here. So here's 1, here's 3. So at 1, it is constant all to the left of 1. And at 3, it is constant 0 all to the left of 3. And it is smoothly interpolates between the two. Right. And so this is a function that you can construct from R to R, and then with some finagling with charts, you can define this using the distance function to get a map, which does this too. Okay, and then we're going to do something similar. So we're going to define a vector field for each I in 1 to n, a vector field xi, which is equal to phi I times, I'm just going to use 1, doesn't matter. Now these vector fields, this collection of vector fields is linearly independent. And so, okay, so you might be like, Jacob, where did you construct a partition of unity? I've constructed a partition of unity only around these endpoints because I'm lazy. Yeah, there's a way to do this using actual partitions of unity, which perhaps I probably should have done. But I was just like, oh, I want to use partitions of unity, which means that I want my points spread out, and I should have just started with the partition of unity, but oh well. Okay. So these vector fields are linearly independent because these open sets that they are defined to be one on are disjoint, right? So note if alpha 1 x1 plus dot 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 plus alpha n xn is identically equal to 0, then alpha 1 x1 at pi plus all the way up to alpha n xn at pi is identically equal to 0 for, sorry, not identically equal to 0, just is equal to 0 for each I, but this is just alpha I xi evaluated at pi. Which is, of course, just alpha I times this by definition. Right? And so the only way for this single vector field to be equal to 0 is if the constant alpha was equal to 0. So this means that alpha I is equal to 0 for each I. Right? So what we've just shown is that for any n, I can construct n linearly independent vector fields. Right? So there's no bound on the number of linearly independent vector fields. So we conclude, wow, my handwriting is getting sloppy. So we conclude is infinite dimensional. So you can modify to do this via partitions of unity by just putting a partition of unity on the space. You define the bump functions the same. The partitions of unity give you bump functions just as part of the definition of partitions of unity. And then you define your vector fields the same way. And you get a similar contradiction argument because these partitions of unity are only locally defined on your manifold, right? That's the entire point of having a partition of unity. And then you say, oh, this partition of unity is equal to 1 over here, but I can find a different partition of unity with a different function, which is equal to 0, right? So that way, right? Yeah, and then you get that these things are linearly independent from this. Yeah, okay, so Wilhelm, that's not how you spell Wilhelm. Actually, I don't know how to spell Wilhelm. Wilhelm defines a cover of regular coordinate balls as a collection of charts, ball of radius 3 centered at 0, comma, phi alpha, alpha and A, such that phi alpha of the balls of radius 1 of 0, alpha in A, is a cover for your manifold M. So the regularity condition is that the smaller unit balls are actually the cover, but the charts that I am taking are bigger charts than charts of radius 1, right? So this isn't a cover by unit charts, even though it is a cover by unit charts, right? It's that, you know, there's a difference between like the fact that the charts have this bigger domain than, and there really isn't that much of a difference. But, okay. Yeah. Yeah, so I'm just using this concept of a regular ball to mean that I'm taking my balls to be of radius 3. That's the only reason that I kept the word regular here. But the reason that Wilhelm defines this is because every single time he defines a cover of regular coordinate balls, the next thing he does is he defines these bump functions, where the function is equal to 1 between 0 and 1, and it is equal to 0 after 3, and then it is smoothly transitions from 1 to 0 between them, right? And so since that's what I wanted to do, I just chose the symbols. Maybe a poor reason to call this regular ball. In fact, definitely a poor reason. Okay. Any other questions, comments, or concerns?
The partition of unity definitions has like, 8 different things you have to show. So, do we need to like, where are we locally finite? And, these conditions are really hard. So I'm just saying, like, I guess we don't officially say partition of unity, and that's why we can get around it. You can just say bump function. You don't have to show the 6 different really particular.
Yeah, isn't the only reason we have partitions of unity so that we can either metrize our space or do bump functions? And since we're not metrizing our space here, we only
Might
need
as
to
well.
care about the fact that we get bump functions out.
Mhm.
Yeah. So if you did what I just wrote here, you'd find a cover of regular coordinate balls as this collection,
Mhm.
right? A lot of the time, what you're going to do is you're going to be like, hey, since my manifold is compact, there's just a finite cover of this, okay? And then that's how you get your finite sum condition, because there's only a finite number of open covers anyway, right? But if you're locally finite, what you can do is if you just define all your bump functions first, but you have like a finite intersection property, like every point is only contained in the, if you have the locally finite condition, which was from qual 0, right? Every point is only in a finite number of your open sets, right? Then you can just turn any collection of bump functions into a partition of unity by dividing your bump functions by the sum of all the bump functions, right? Right, you define a new function, and I'm running out of Greek letters, so we'll call it delta for partition of unity, right? This is going to be phi I divided by the sum of all phi I, right? And this sum will be a finite sum because each of your points is only in a finite collection of open sets. Right? And then you get the partition of unity thing where you want that the sum of all of your points equals 1, right? That's another thing from the partition of unity, is that you want that, like, if you take any point and you take the sum of all the open sets which contain that point, you get 1. Right? But you can do this by just dividing by the sum of over all of your bump functions, then you just get this, like, it regularizes your bump functions. So there are a lot of people, there are some, I don't say a lot, but there are some textbooks that just define a partition of unity as the sum is equal to, is finite everywhere, right? And then they do this trick to get a sum equal to 1 when they need it, like when they're defining a global metric on the space, right? You define a local metric on the space, you multiply that by a partition of unity, which sums to 1, and then you get a global metric on the space. Like Raoul said, you use partitions of unity to make metrics.
I have a quick question because you mentioned the finite intersection property. Just remind me, so I didn't end up remembering what it was. I ended up like just trying a bunch of things until I could find something that I could work with. So I ended up settling on the finite intersection property for that that one where you show in that same mock qual, I think, that for any point in the complement, or for any point, the intersection of a open set around that point with the collection is it intersects only finitely many of the elements in the open cover. Is that correct?
Yeah, so if I recall, a collection of subsets of X, collection of X, has the finite intersection property if, let's see, can I remember this or am I gonna have to Google this? I think it's just that if for all x in x, x intersect y alpha equals the empty set for all but finitely many alpha. I don't know, but it might have to be every neighborhood intersects only a finite number of these. So this is my guess. Let's look it up on Wikipedia. Well, this is not what. No, it's a locally finite family. Since it's a locally finite family, then it does definitely. So I don't want to write the finite intersection property because that's a different property. And if it's a locally finite, then it does have an open condition because it has to. Okay, so this was wrong, but that's because I was remembering the wrong name. Is called a locally finite collection. The word locally tips you off here, right? Because locally always means the same thing. Yeah, we'll just, if for all x and x, there exists U open with x in U such that U intersect Y alpha is equal to the empty set, except, no, that's not how you spell except either. For finitely many alpha. Okay. Or in other words, every point has a neighborhood where that neighborhood only intersects a finite number of points. Right?
Cool, sweet. Yeah, so I had for all U instead of there exists U, but it ends up not mattering because I just changed like a period to a comma and it works.
Yeah. Yeah, I think you might get in trouble with for all because I could let
Oh, you do.
be the
You can
entire
just 100%.
space.
Yeah,
Right?
exactly. You just take the whole space.
Yeah.
Which is like dumb, but yeah, if you just take there exists and then just say instead of, oh, take an arbitrary one, just pick the one that makes this statement true.
Right. Yeah. Yeah. And because this is local, we could reframe it as, instead I could replace this with for all U open, or just so that we don't have to change the later. I can say for all V open with X in V, there exists U open with X in U contained in V such that rest of this argument is the same. Right? And if I were to guess now, this blue condition is probably what I would guess, because every time we define something which is locally blank in topology, we always mean this definition, right? Between every open set and a point, you can find a open set which satisfies blah, blah, blah property. The only time that this isn't the case is in the definition of locally compact. Local compactness is almost this definition, except that you have that the closure of U is compact. Because normally open sets are compact. So you turn it into a closed set first by taking its closure, and then you say that it's compact. And that's how you get locally compact. But yeah, like locally path connected means that between every open set and every point, there's a path connected open set between, right? Locally connected means that between every point and every open set, there's an open connected set in between, right? Like every time you're locally blank, it means this condition where the middle set has that adjective. So.
Can you explain, I guess, why, oh, sorry. Can you explain why, like, you need that intermediate open set a lot of the time, most of the time?
Yeah, so if I wanted to be locally path connected, but I didn't have this intermediate set, then I could just take X to be the entire space if I'm globally path connected. So we've talked about the example of like the topology sine curve, right? Where I had like this edge and then this like sine curve, which is oscillating more and more and more and more and more and more, and more, right? So it's like sine of 1 over X union Y axis, right? This is not path connected, and it's also not locally path connected. But now I can make this globally path connected by just connecting the tail end to the y-axis using a right bypass. So now a path from here to here, I just go backwards until I get to the overpass. But if I take a small open set around here, this is not path connected, right? Because it's going to intersect some of these up and downs. And there's going to be no way to get from the sine curve part to the y-axis curve part with a path. Right? So that's why you need that, right? You want to say no, right? And we think about these as like with like the epsilon ball definition, right? That I can always find arbitrarily small path connected open sets, right? That's what we want locally path connected to mean if we think about epsilon balls. I want to be able to find tiny, tiny epsilon balls which are path connected, right? And that's what this condition is trying to emulate, right? I can always find and another way that you can define locally is that you can always replace locally with has a basis of whatever, right? And this is equivalent, right? If I'm locally path connected, then there exists a basis of path connected sets. Same thing.
Jacob, before we leave the vector field stuff, can you go over what a derivation is? Or
Oh
yeah.
boy.
Sorry,
Probably not.
A derivation is a thing that behaves with the chain rule.
Yeah. Oh,
Well,
okay,
I mean,
yeah.
there's that, and then there's like a thing that's also like a germ, and things like that.
Right, okay. So technically, the elements of a tangent plane of a vector are derivations. Right? A derivation is a linear map, which we call V, which takes a C infinity function on your manifold to R. Such that, let's see here. Yeah, so rule's right, it satisfies the chain rule, such that for two derivations, V and W, we have that AV plus B W, no.
Isn't it like V of FG is Well, it's a derivation at P if V of FG is F of P, V of G plus G of P, V of F.
Yeah,
And Shauna, your question about the germ stuff, Wilhelm basically says you can essentially ignore that because it's just the author being fancy.
Hmm.
Right? Like, yes, it's necessary, but he's like just being a dick about it. Because like you could phrase it without like defining what a germ is. It's just that because the thing is that you only care about the local properties, right? Because
Mhm.
there's like no one cares when you take a derivative, no one cares about what happens far away from your point. So you only care about functions that are defined locally. And then when you do that, you then have to like make sure it's actually well defined without to sort of like, because you want to talk about derivations to create vector fields, right? And so you take, oh, well, take curves. There are multiple ways to define a curve where at a point, the tangent vector is the same. So let's put on an equivalence relation that makes it so that's true.
Mm.
So yeah, germ is just so that we have locally defined functions with that equivalence relation.
Nice. Thank you.
trying to use this time to look up what the, oh, there's the bump function. Okay, anyway. This probably isn't
using-
even worth Googling.
Are you in Lee or are you?
I'm in Lee because that's where I know where things are.
Yeah.
The new textbook, I don't know.
The new textbook happens to be 1,000 years old, so.
Oh, okay, great,
Everybody hates it. Might as well look at the Lee one, right?
great. Oh, boy. Oh man, at the beginning of the quarter, at the beginning of the summer, I knew all this stuff. And I remember that I talked to someone in office hours that was just like, this is what a derivation is. And I was like, boom, I know exactly what derivations are. But that was like the beginning of summer. How am I supposed to know what that is now?
Yeah, like I think the thing is, right, like I think as Anthony's saying,
It's somewhere in
say it's a-
chapter 3.
you say it's a derivation if you want to talk about it from the axiomatic standpoint of
Yeah.
this is very clearly going to form a vector space. So they are, like Anthony says, they just act the way you want them to. And this forces you to have a vector space structure because that's how you define it. And then the other way is the so-called geometer's definition, which is what I was talking about with germs, where you say, oh, well, I want to define a vector at a point so that I can talk about curves going through that point, having a tangent vector, that vector. And so you get around it by doing this germ thing and throwing in equivalence relations, yada, yada. And then it turns out these are equivalent definitions. And one of them is just more useful for some cases than the other.
Huh, interesting. The only requirement that we have for derivation is that it satisfies the product rule, which makes sense. The chain rule doesn't make sense for
Right,
these
that's the rule I
functions.
meant. I just,
Yeah.
when we write it in this abstract way, I view that as the chain rule because I'm stupid.
No. Hmm. Yeah, because we've done nothing here with derivations. I'm afraid he's going to be like, qual, 6 problems about derivation. He's going to talk to Schultz to make a homology problem about derivation. Maybe it's not that bad.
Yeah,
Yeah.
when he did this class last year, he only really went over the definition that was like equivalence classes of curves.
Yeah, that is Wilhelm's preferred definition. That's because he's a geometer and he wants to talk about things in terms of curvature. So he's always talking about curves.
Yeah, Brocker and Janich says basically the only reason we give the definition in terms of derivations is that it is much easier to claim that this is a vector space.
Mhm.
Hmm.
Yeah. Yeah, and then at some point you say, hey, this construction and this construction are isomorphic.
Yeah, and the proof of that was maybe just ugly because the typesetting is disgusting, but I hated it.
Yeah. Mhm.
Yeah, one thing that's nice about this class is that you never have to compute actual derivatives of functions.
Right, yeah. So
That
derivations are
stuff that you
equivalence
do in 10A that you never do in
10A.
this class.
So derivations are equivalence classes of curves. You can just keep it like that. Right, Anthony, is that what you said?
Yeah,
You said?
yeah.
Yeah. That's fine with the germs and all that stuff. Okay, sounds good. I don't know if anybody had anything else. Jacob, I would like Anthony's counterexample. Kath and I were still like, wait, what? With the two sheeted cover with a finite or with an odd fundamental group. And you did something once, you were like, Shanna, just like take the circle and cut it into
Oh.
threes and sew it.
Yeah, so
Katie and I are like, wait, what?
yeah, so we can talk about that. So if I take a disk, right, so this is a B2, and I identify opposite points, antipodal points of just the boundary, right, so that means that I take this edge going this way and this edge going this way, then what I get is RP2. And the fundamental group of RP2 is Z mod 2Z. Why is this? Because this here, this red path, alpha, is a non-contractible loop. Right, because it goes from this point and this point are identified. So it does start and end at the same point. So it is a loop. But there's no way to find a homotopy between this path and the constant path. Okay. Any way that I try to homotope, I'm stuck starting here and going here. But if I do alpha squared, which I can draw as this, okay, so this entire green going around twice is alpha squared. It's alpha composed with alpha. This is contractible. Right, because I can now contract this through the center disk. Right. So RP2 is generated by this gamma, and gamma has order 2. So now what we're going to do is we're going to.
Why is it? I guess I'm having, like, I remember doing this problem when we cut out like the disk in the middle and all that construction, but I guess, so wait, why is the red loop not contractible?
Yeah, other than just looking at it and being like, how would you contract this? Let's see. Another way that you could look at this red loop is you could look at this red loop as a loop which just goes straight through the center of the disk to the other side, right? This is the same because I can just deform it up to the edge, right? And because in path homotopies, I have to keep the endpoints fixed, right? I have to do some, right? I can't move this point anywhere.
I mean, my issue with
Yeah.
trying to like visualize it is those 2 points are the same point.
Right.
So like, you're not actually like, in my mind, yeah, you can deform it without moving anything, because when you like identify those 2 points, just contract them down on the inside, but then that actually doesn't work, because if you do that, you're sort of kind of turning it into an S1, and it's just dumb. It's like, I hate visualizing this. I can't visualize RP2 like this.
Right.
So I just kind of have to take it at your word. Or do the Mobius strip construction.
Yeah.
I think I'm seeing it the same way as Raul. Like it's the same point. You connect them together, and then it just. But I also believe you that it's not contractible.
Yeah.
Yeah, because like in my head, what I'm sure I'm doing like as mental imagery is I'm not using the right identification. I'm identifying the entire perimeter to a point, and then you can certainly contract this because that's S2.
Yeah. Yeah, these 2 opposite points are identified, but only opposite points of the boundary are identified, right? So I can't move these points, and I'm not supposed to move these points because they're the base point of my path, right? So the only thing that I'm allowed to move this path is that I'm allowed to move this path in the center of the disk, basically, right? And one way to see that is that if I do any homotopy which does cross the boundary of the disk, right? Like I homotope this to say something weird, which does like this, right? So like this is the same path, but it's not the same path. Like I could like, let's see, if I homotope this up, I can do something like this. I think this is the same path. Yeah. Right. Yeah. Yeah. So I guess that like, and then you could be like, oh, cool. Now I can pull this end this way and this end this way, right? And then I can like bring these 2 points to, right, a base point, then maybe I can homotope it down. But like, if you try to do this, then this bit gets bigger, right? So like if you do like
You just
this,
get back to the
this,
equator
then
thing.
this becomes like this, right? So I guess that one thing to do is that if I take this path and I try to homotope a piece of it over the boundary to try to do something clever, I can only homotope this in pairs across the boundary, right? Like I can't intersect, I can't pull half a single strand. I have to pull 2 strands over, if that makes sense. And so then I always get like this bit on the other side. Okay? So like this path, this is not homotopic to this path. Like, I don't know if this phrasing makes sense. So Anthony had to leave by Anthony. Right, because what did I do here? I just grabbed this string and I pulled it up. Okay, and I grab the string and I pull it up, then I get this picture, right? The 2 sides of the part that I'm holding are still dangling on this side of the circle. And then over here, actually, I think the orientation reversed, but whatever, because the way the identification works. Yeah, the orientation definitely to reverse, right? Right, this point goes to this point, which then goes to this point, which then goes to this point. So, but I can't get this baseball picture. And one way to see this baseball picture is that if I bring this point this way and bring this point this way, then what I actually have is 2 copies of this path. And, or if instead I brought this point this way and this point this way, then what I actually have is just like a constant path, right? Which is another proof that if I have 2 copies of this single generator, I get a constant path. I can homotop to a constant path, right? Anyway, to answer Shanna's question before it gets too late, to get a group that has fundamental group of X is Z mod 3Z, you do the same deal, except instead of identifying antipodal points, you break up your disk in the boundary of your disk into 3 pieces, and you identify this edge and this edge and this edge. Yeah. And then you get the same story, right? If this is my gamma, this gamma does not homotope to the constant path. 2 copies of gamma is the same. I can take this point and homotope it down, so that way I can get gamma squared, which is this path, and 3 copies of gamma. So if I go backwards this way, so this is another gamma, that's a gamma, and that's a gamma. Well, I can just take this corner and homotope down, and I can take this corner and homotope down. So I get gamma cubed is the same as the constant. And so you get that when you identify these 3 edges, you get a space that has the 3 as its fundamental group, and breaking up the boundary of the circle into n pieces and identifying n pieces gives you a space that has fundamental group Zn.
So for this one, can you also use like the tactic where you cut out the middle disk, or does that not work anymore because you no longer like actually have a Mobius strip around the outside?
Yeah, so this is gonna look, okay, so one thing to note about this is that this is not a manifold. Right? Right, if I take a neighborhood of this boundary where I've identified points, right, it's gonna look like how do I draw this? Yeah, it's gonna look something like this, right? Because I'm gonna have like, and if I draw like, here's the red bit, and here's the green bit, and there's a black bit, right? Then like, here's the black bit, and here's the green bit, and here's the red bit, right? Like it's got, right, like if I just look at like a neighborhood of the edge, I'm gonna have 3 2-dimensional planes all intersecting my edge, right? So I'm gonna get like this tripod behavior. And this is not a manifold because any neighborhood of where these 3 planes intersect is not going to be Euclidean, right? Because Euclidean space does not have 3 intersection planes, right? So, and this is going to be true for any n greater than or equal to 3. This space is not going to be a manifold. There do exist manifolds that have odd finite fundamental group. These are called lens spaces. And they're constructed as quotients of like higher dimensional space. They're not surfaces, they're higher dimensional manifolds.
What was that name called? You said higher dimensional manifolds?
Yeah, they're called lens spaces.
Lens,
I
yeah.
believe they're quotients of 3 space, but
Weird.
don't quote me on that. I don't study 3 manifolds. I study triangles, and then occasionally I do whatever's on the topology wall.
Fun.
Oh, somebody posted something in the chat. I missed it. Yes. Yeah, so Anthony said a derivation is a vector field that acts on C infinity M like a derivation in the sense just described. Yeah. Yeah, because a vector field is a choice of derivation at every point. Because a vector field is a choice of tangent vector at every point. And what a derivation is trying to do is it's trying to generalize what a tangent vector is. Okay? And then tangent vectors due to functions, or sorry, derivations due to functions, what tangent vectors do to functions. Namely, if I give you a function and a tangent vector, you can compute using multivariable calculus the directional derivative of that function in that direction. So that's what happens when you stick a derivation in front of a function. You're generalizing the directional derivative, right? By feeding this vector a function and it spits out a number which represents the derivative in that direction. And then a vector field just does that everywhere.
Yay.
Yay. And I say just does that everywhere. I say if that's not totally a non-trivial thing to construct and work with and do problems on, but you know. Okay, so we had a bunch of problems that were listed up here on the top of the doc that we did not get to. Namely, all of the problems on exercises to know. Okay, so for next week, since we are technically out of time, I can write another mock qual. We can just talk about more problems from prior stuff that we haven't got to talk about. What are y'all feeling?
I like the mock qual, and we're doing the other exercises to know anyway. So just the more problems help me, but it's up to what everybody else thinks. We have a pile of the exercises to know, and then we're like, what's the new mock qual? It's kind of like exciting. I don't know, there's no reason for it.
Okay, I was hoping that the mock qual was going to be the thing that y'all voted for, because I've already written the mock qual. So now all I have to do is compose it.
I vote mock qual then.
Mock qual voted.
But I'm totally fine. I can also just upload the mock qual, and we just don't talk about the mock qual next week. Like maybe people are just like, okay, yeah, mock qual, schmock qual. Let's talk about these problems instead. This might be the last mock qual that I write, though.
Okay.
Just because like we have one official week left and then one makeup session left. But after this mock qual, if you are looking for other mock quals, Jonathan last year wrote 3, and he has several problems on his mock quals, which I did not put on my mock quals. So you can look at those mock quals. Cool. Yeah, so looking at the schedule, we have 3 days of meetings left. We've got our 2 regular meetings next week, and then we have our makeup meeting the Tuesday after that. And then as a quick announcement, I'm not going to have my office hours tomorrow. I can do some makeup office hours either next week or the week after that, the same week that we have the makeup meeting, but my parents are flying into town tonight. So I'm picking them up from the airport and I'm spending time with them tomorrow.
Okay.
All right, cool.
Right.
Well, thanks for
Thank you,
meeting,
Jacob.
everybody.
Hi,
Hopefully
thank you
this
so much.
was some level of useful.
Yes, please post those when you can. Yeah.
Yeah, and I'll post these when I'm done. So,
Okay.
all
Have a
right,
good time with your family.
Yeah, have fun.
later, everybody. Bye-bye.